So we're at a place where we can analyze a reaction graphically. Let's say we have a reaction where A is decomposing into B plus C. Those are our two products. Our reactant is A. And we look at that graphical representation. We know about this particular spot. That's the amount of A that we have to begin with. And then we have time on the x-axis, which is proceeding in this direction. And we understand that the reaction is going to be going at its fastest at the initial concentration. That's why we do rate law experiments using the initial rate method, because at the beginning of the reaction, you have the highest concentration of A, you have the most collisions, and so you're going to have the fastest point in the reaction at the initial, at the start, at time zero. So you actually take the instantaneous rate at the start of the reaction at time zero. So we know about that. We know that the reaction slows down as it proceeds in a forward direction because the concentration of the reactants are decreasing, but we don't yet know what the rate law is. That is, we don't know what the exponent is. Is it first order? Is it second order? Or is it third order reaction? So what is that exponent? Wouldn't it be nice if there was some mathematical manipulation that we could do to the concentration of A versus time that actually gave us a way to see into whether or not this was a first or, let's say, a second order reaction? And the fact of the matter is there is. So what we're going to look at right now is the first order integrated rate law. And we're going to take this reaction and we're going to express the rate as rate equals K times A to the M power. Well, if it's a first order reaction, we know that M is going to be equal to 1. If it's first order, M will equal 1. So a first order rate law can be given by the equation minus dA dt equals K times the concentration of A, which can be rearranged. We'll multiply both sides by dt and divide both sides by A, which will give us minus dA over A is equal to K dt. Now we'll just take the definite integral from the initial concentration A naught to A at some times t, and dA over A is simply the natural log of A, and we'll evaluate it between those 2 points. And we'll do the same thing on the right side of the equation, evaluating it from time 0 to times t, which will give us minus k, parentheses t minus 0. We're just evaluating it between these 2 points, which is just going to give us, after a little bit of rearrangement, the natural log of A at times t equals minus kt plus the natural log of A naught. This is what we know as the first order integrated rate law, which you might recognize has the equation of a straight line. We can go ahead and plot the natural log of A at times t versus time, and what we get is a straight line with a negative slope. Now the reaction has become more transparent. We can instantaneously see that if we plot the log of the concentration for any first order reaction on the y-axis and time on the x-axis, that we will get a straight line with a negative slope. And not only that, look what we have for the slope. The slope is the negative of the k. For a first order reaction, once we plot the log of A at times t, so for a first order reaction, plotting the log of A at times t, we get the y-intercept as the log of A naught, the initial concentration, and then a straight line with a negative slope, which is equal to the minus of the rate constant k. Now you might be wondering, is there an integrated rate law for other reactions? And yes, there is. For a zero order reaction, we simply plot the concentration of A at times t versus time, and we will get a straight line with a negative slope, and that slope will equal the negative k with the y-intercept. So what does it mean for a reaction to be zero order in a reactant? What that means is that even though that reactant has to be present for the reaction to take place, for it to go forward, changing the concentration of that reactant doesn't change the rate of the reactant. That's why we can simply plot the concentration of the reactant at times t versus time and get a straight line. For a zero order is A at times t equals minus kt plus A naught. For a first order, you're already familiar with that, we plot the natural log of A at times t versus time. We get a negative slope straight line with a negative k equaling the slope, and the log of A naught is the y-intercept. If a reaction is second order in a reactant and you plot the inverse of the concentration of A versus time, what you're going to get is a straight line with a positive slope, and that positive slope will equal k. The integrated rate law for a second order reaction is equal to 1 over A at times t equals k, a positive k, times t plus 1 over A naught. Now this is a second order reaction. So now that you know the difference between a plot for a zero order reaction, a first order reaction, and a second order reaction, we're going to go ahead and we're going to use the first order integrated rate law to solve some problems. I will not be asking you to solve any calculations with either the zero order or the second order equation, only using the graphs to recognize whether a reaction is zero order or is second order or is first order. But with the first order integrated rate law, we're going to solve problems because it's a very handy rate law to have. Here we have data that represents a change in pressure for the isomerization of methyl isonitrile. And we can use pressure in place of molarity because if you recall from gas laws that pressure is equal to the number of moles times R times T divided by the volume. And R and T are kept at a constant temperature, in this case 215 degrees Celsius, which really just leaves us with moles divided by volume. And so you can relate pressure with molarity. And so we're using pressure as a unit of concentration in a gas phase reaction. If I simply plot the pressure versus time, I wind up with a curve. And the curve doesn't allow me to see whether it's a first order reaction or a second order reaction. So if I plot the natural log of the pressure versus time, instead of just plotting the pressure versus time, I get a straight line with a negative slope. That tells me that first order kinetics apply. I can use the integrated rate law to do all of my calculations, and I can simply calculate the slope of the line. I know that it's going to equal the negative of the k, which allows me to determine the rate constant just from the graph. So here's the previous graph for the isomerization of methyl isonitrile. Let's go ahead and identify these 2 points. Here is x sub 1, that's time 0, and y sub 1, that's 6.22. Now remember, that's the natural log of the pressure. And over here we have 15,000 seconds, which is x sub 2 on the x-axis, and y sub 2. We'll go ahead, we'll calculate the slope, and the slope, m, remember, is going to equal the negative of k. That's going to be the negative of k, and then we just need to take the positive. So we're going to have y sub 2, which is 3.11 minus y sub 1, 6.22, and we're going to divide that by x sub 2, which is 15,000 minus 0, which is x sub 1. And when we do that, and the result is minus 2.07 times 10 to the minus 4. Now, that is the slope of the line. The k will be the positive of that slope, which is 2.07 times 10 to the minus 4. Now, since this is first order kinetics and our unit of time is seconds, we know that our units on our rate constant will be per second, or seconds to the minus 1. And you guys know that s to the minus 1 is just 1 over seconds. And anytime you have a first order reaction, the units on your rate constant will always be per unit of time. Now that we know the rate constant, we can use the rate constant to come up with the half-life for a reaction. Remember, the half-life is defined as the time required for the concentration of a reactant substance to decrease by half its value. So for instance, if this is our original concentration at time 0 and the half-life is 12 seconds, it'll take 12 seconds to get to 50% of whatever the starting value was. And then another half-life goes by and we now have 25% of our original concentration. Another 12 seconds, another half-life goes by, we've got 12.5% of our original concentration. And once again, we just keep on going down to 6.25% and so on. So this is the first half-life, here's the second half-life, here's the third half-life, here's the fourth half-life. So in one half-life, we have 50% remaining. 2 half-lives go by, we're down to 25%. The third half-life goes by, 12.5%. Fourth half-life goes by, 6.25%, and so on. So here is a quick derivation of how you can use the first order integrated rate law to determine the half-life equation for a first order reaction. Since we have a starting concentration of A naught, or A at time 0, we can imagine that when one half-life goes by, that the concentration at times t will simply be 1/2 of the starting concentration. So the natural log of 1/2 of A naught is equal to minus kT 1/2 plus the natural log of A naught. We'll rearrange the equation a little bit. Go ahead and subtract the natural log of A naught from both sides. Use our log rules. And once we've subtracted the natural log of A naught, we use the log rules. We rearrange the equation as the log of 1/2 A naught divided by A naught. A naught cancels, which gives us the log of 1/2 is equal to minus kT 1/2. That just leaves us with the negative of the log of 1/2 is equal to kT 1/2, and the negative log of 1/2 is 0.693. We could actually rearrange that, do the natural log of 2 positive, which would give us the same value, 0.693. You can plug it in your calculator and check it out. And then we rearrange it into this. The half-life for a first order reaction is equal to 0.693, which is just the log of 2, or the negative log of 1/2 divided by K. And this, if you'll notice, doesn't contain any units of concentration. That's because for a first order reaction only, the half-life does not depend on concentration. It's independent of concentration. So T 1/2 is equal to 0.693 divided by K. You need to remember that equation. The half-life for a first order reaction, T 1/2, is equal to 0.693 divided by K. Remember this. So you now have two methods for determining the value of K. You could determine the value of the rate constant for a first order reaction from the slope of the line. You could also do it for a 0 or a second order reaction, but we're only focused on first order reactions right now. Therefore, the half-life of the reaction can be determined using this equation. If I know what K is, I can determine the half-life for a first order reaction. Also, if I know the half-life, I can determine K. So I could rearrange this expression, solve for K, 0.693 divided by T 1/2. If I know the half-life, I can solve for K. The first order rate constant for the decomposition of a certain antibiotic in water at 20 degrees Celsius is 1.65 per year. If they didn't tell you that it was a first order reaction, you would know because the rate constant units are per unit of time, or 1 over years. So K is equal to 1.65 per year. If a 6.0 times 10 to the minus 3 molar solution of the antibiotic is stored at 20 degrees Celsius, what will its concentration be after 3 months? Now, if you know it's a first order reaction and you have an initial concentration, so for instance, this concentration is A naught, and you want to know what the concentration is after some period of time, and we're talking about 3 months. So I think years is the easiest conversion to make. And so let's see, 3 months, and how many months in a year? There's 12 months per year, which is simply equal to 0.25 years. So that's time. Time is equal to 0.25 years. So now that you know that time is equal to 0.25 years, that's how much time is going to go by. We want to know how much of the antibiotic is left. And that's an important question to ask because antibiotics are perishable substances. Since it is a first order reaction, we're going to go ahead and use the first order integrated rate law to determine how much of the reactant will be left after 3 months. And it's going to be a straightforward calculation. So we have the log of A at times T is equal to minus 1.65 per year times time, which is 0.25 years. How much time goes by, plus the natural log of the starting concentration. 6.0 times 10 to the minus 3 molar. So that's how much we start with. So what we're going to solve for is the log of A at times T. And when we solve this expression in our calculators, we wind up with minus 55.28. Now, this is considered to be unitless because it's the natural log. In order to get rid of the natural log, we need to take the antilog of the natural log, which on your calculator is a little key E, and that is the antilog to the natural log. So we'll go ahead and take the antilog of this term. What that's going to result in is the concentration of A at time T, which gives us 3.97 times 10 to the minus 3 molar in concentration. So the first order integrated rate law is very handy for finding the concentrations of reactants after a certain amount of time has gone by. It's also very handy for solving for K, and it can also be very handy for solving for time, or the original concentration that you started with. You could also solve problems in a similar way using the second order integrated rate law. I am not going to ask you to solve any quantitative problems, only to understand that if you plot the inverse of concentration versus time and you get a straight line with a positive slope, you're looking at a second order reaction, not a first and not a zero order reaction. You can see that because if you plotted the natural log of, let's say, this reaction, which is the decomposition of nitrogen dioxide to nitric oxide and oxygen, you would get a curve, which indicates it is not a first order reaction. How do you know that it's not a first order reaction? Because you plotted the natural log. You didn't get a straight line with a negative slope. You got a curve with a negative slope. If, on the other hand, you plot the inverse of nitrogen dioxide, you get a positive slope and a straight line. You know that it is a second order reaction.